Okay, so in this video, we're going to be having a look at the gradient function, and we're looking at example 3 here. So this time, we've been given an equation, which is y equals to 2x cubed minus blah, 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 okay? And it says, show that the curve has a stationary point where x is equal to 2. So we first need to think about what it means to have a stationary point. So I've drawn a little visual aid down here to help us out. So a stationary point is any point where the graph sort of hollows out, okay? And at these stationary points then, I can always draw a horizontal line. So let me just draw in my horizontal line. Okay, so wherever you can draw a horizontal line on the graph, that is your stationary point. So what we know then is we know what is the change of y at these points. Okay, so there is no change in y. The change in y is 0 because it's a horizontal line, which means that a stationary point has dy by dx equal to 0. Okay, so the stationary point implies dy by dx is equal to 0. Now that's really important, so always write that down for me. Okay, so here then I've drawn the table and the little cycle from video 1 just to help us out here. So this time we've been given y, and I want to find dy by dx because then I can set it equal to 0. So in order to do that, I'm going to have to differentiate this time. So from y to dy by dx is differentiating. So let's do this. So the differential of y is dy by dx using our little cycle. Now, to differentiate, we need to times the power by the number in front. So in this case, it's going to become 6. And then we take one from the power. So it's going to become 6x squared. Let's do the same with the next one. Times by the power. So we're going to have minus 18. And take one from the power, x. Okay, and the last one, imagine this is x to the power of 1. So timesing by the power gives 12. Taking 1 away gives x to the power of 0, which is 1. So it's just 12. So here we don't need a plus c. We only need a plus c when you integrate. Okay, so now we know we're looking for the stationary point. And as we discussed earlier, the stationary point is when dy by dx is equal to 0. So if I set this equal to 0, 0 equals to 6x squared minus 18x plus 12. And simplify this equation, let's divide through by 6. I'm going to have x squared minus 3x plus 2 equals to 0. And upon factorisation to find out my answers, I'll have an x, a 2 and a 1, and they're both going to be negative, giving me answer of x is equal to 2 and x is equal to 1. So as you can see here, a stationary point is at x is equal to 2, which is what is asked in the question, but we've also found another stationary point at x is equal to 1. Okay. So the last thing then we need to do for part II is we need to determine if it's a minimum or a maximum. Okay, so there's a little technique here in order to find minimum and maximum. So to find the minimum and maximum of a single value, so our x is equal to 2, you need to differentiate again. So to find d squared y by dx squared. Now this seems a lot more complicated than it is. So when you do this, you're going to just differentiate your dy by dx again. So let's times by the power to give us 12. Take 1 from the power, gives me just x. Times by the power here, we're going to have minus 18. Okay, so we're looking at the point where x is equal to 2. So let's set x equal to 2. Which gives us, okay, d squared y by dx squared is equal to, let's times this out, we're going to have 24 minus 18, giving me a value of 6. Okay, so there's a last thing that I want you to have a think about here. So this is our general rule for minimum and maximum values. Okay, so if d squared y dx squared is greater than 0, it's a minimum. And if d squared y dx squared is less than 0, it's a maximum. So it's a little bit reversed here, okay? So try and have a look through these for me and apply them to some other questions. So in our case, d squared y dx squared is equal to 6, which means it's greater than 0. So here it's going to be a minimum. Okay, and we're done. Perfect. Really well done.